Alright, today we're going to talk about the rational root theorem. Sometimes we will not be told what to divide our polynomials by in order to find the roots. For situations where we need to find all the roots, we can use the rational root theorem. The rational root zero theorem gives a list of possible rational zeros of a polynomial function. So remember, these are just the possible zeros, and they're only the possible rational zeros. Not every number in the list will be a zero of the function, but every rational zero of the polynomial function will appear somewhere in the list. Most of these possible zeros will turn out to not actually be zeros. So the rational root theorem states, if f of x equals, and this is a polynomial equation right here, and it has integer coefficients, then every rational zero of this polynomial f of x will be of the form of p over q. What is p over q? P stands for factors of the constant term, which in this case would be your a sub 0, over factors of the leading coefficient, which is your a sub n. So let's go ahead and practice this. So let's list the possible rational zeros, which I usually denote as PRR of f of x below. So we have our constant, which is 6, and our leading coefficient, which is 9. And so when we do our P over Q, we're listing factors of the constant term over factors of the leading coefficient. And so remember, we don't know which ones are plus or minus because we don't know the signs in between. So we're just going to do plus or minus for all of them. So factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, because 1 times 6 is 6 and 2 times 3. And then factors of 9 would be plus or minus 1, plus or minus 3, and plus or minus 9. So then we just want to write all of these factors out. So we're going to take the numerator and divide it by our denominator factors. So that means that our possible rational roots are going to be, and I don't like writing plus or minus in front of them all. So if you want, you can just put the plus or minus in front and use parentheses. So you're going to have all these numbers over 1. So that would just be plus or minus 1, 2, 3, and 6. And then all the numbers you are dividing by then 3. So you would have 1/3, 2/3, 3/3 is just 1, and 6/3 is 2. So we don't need to write those because we already have 1 and 2. And then we're going to divide all these numbers by 9. So the next one would be 1/9, and then 2/9, and then 3/9 is 1/3, and 6/9 is 2/3. So we don't need to repeat those because we already have them. So this is the list of the possible rational roots. So why do we do that? Is because listing these possible rational roots is going to help us find all the zeros. So that's what we're doing next. We're going to find all the zeros in the polynomials. So the first step is to list the possible rational zeros. So looking at this polynomial equation, we're going to do step 1. So we're going to list the possible rational zeros. So remember, we have factors of p over factors of q. So this is the constant. And this is our leading coefficient, which is just 1 if it's no number in front. So we want factors of 90 over factors of 1. And if you have a hard time with your factors, remember, you could always use your calculator to help. So if I go to my y equals, I can plug in 90 divided by x, and I can go to my table, second graph, and 1 and 90, 2 and 45, 3 and 30, 5 and 18, 6 and 15, etc. So that's how you would find your factors if you don't know. So in this case, we have plus or minus factors of 1, 2, 3, 5, 6, and then if we keep scrolling, 9 is where it starts to repeat because you see you have 9 and 10 and 10 and 9. So 9, and then if you go back up, we can get the other factors by looking at them. So 9, 10, 15, 30, 45, and 90. And if it helps you to write 1, 90, 2, 45, 3, 30, that's fine too. I just always usually try to write them in order. And my factors of my leading coefficient are just plus or minus 1. So this makes the possible rational roots easy because we're only dividing by 1. So it's just really plus or minus the factors of 90. So 1, 2, 3, 5, 6, 9, 10, 15, 30, 45, and 90. So now that I've listed the possible rational zeros, I'm going to test the zeros using our calculator to find the actual rational roots. So I'm going to underline this right here. So I always label this ARR for actual rational roots. So that means that these are the ones that actually work when we plug it into our calculator. So in order to do this, we're going to go to our y equals, and we're going to plug in our polynomial equation into our y equals. I already have mine in here, but if you don't, you can just go ahead and pause the video and plug it into your y equals and then unpause it when you're done. So once you have it in your y equals, I like to look at the graph. So I'm going to hit zoom 6 for a standard window. Now, this is a polynomial of degree 4, which means that I need to find 4 zeros. So I'm just going to make a note that this is a degree of 4. So by the fundamental theorem of algebra, we should have 4 roots or 4 zeros. So for this one, I know that the end behavior, so since this is even positive, both ends are going up, which means I have a minimum that goes really down below here. So we're not really worried about where the minimum is for these graphs because we're not graphing the whole sketch of this. We're just looking to figure out the zeros. So when I'm doing that, the best thing that you can do is look at your possible rational roots. The highest possible rational root that I have is 90. And because it's plus or minus negative 90. So I'm going to change my window so that I'm looking at the highest and lowest possible rational roots so that I know that I'm not missing any from my window right now, which is just looking at x values from negative 10 to 10. So I'm going to plug in negative 90 here, and then I'm going to go to 90. And then when I hit graph, it's going to make it so that I can see if I'm missing any zeros out here. And I can tell that it doesn't look like I saw any other zeros there. And this is not a very good window. So that means just those 2 roots are the only ones that we have. So I'm going to hit zoom 6 again for a standard window. So it's nice to look at the calculator like this when you're finding the zeros because we don't really want to try all of these factors. That might take us a while. Could you do it? Yes, but it might take a while. So let's look here. It looks like we have negative 1, negative 2, and I just realized that I accidentally put plus 3x cubed, so I need to change that, or minus, and I need to change that to plus, sorry. So that should have been x to the 4th plus 3x cubed minus x squared plus 27x. I'll just check the other one's minus 90. So sorry about that. I'm going to go back to my graph. There's no other zeros farther out, even though I changed the equation. I've already tested it, so we're just going to skip that part for now. So we have negative 1, 2, 3, 4. It looks like we're actually at negative 5. So the best way to test this is just using your calculator window. If you go to second trace and value, then you can just plug in negative 5 and enter. And that shows us that the y value is 0. So that's an actual rational root that we have. Then on the other side, it looks like we have 1, 2. So these are nice because these are not fractions that we're worrying about. So that makes it a little easier to find the zeros. So second trace value, and if we hit 2, enter, I get my other 0. So if we didn't see any other factors between negative 90 and positive 90, what does that mean about the other zeros? It just means that the other zeros are going to end up being imaginary. So how do we actually find them is what we need to look at next. So the way that we actually find them is by using synthetic division, because what does synthetic division do? It factors your polynomial equation, because if I look at this polynomial, I have 1, 2, 3, 4, 5 terms. So with 5 terms, we don't know how to factor this, and so that's why we're using our synthetic division to help us factor it. But if it was something that we could factor, you would always want to do that first because it's faster. Another way you can find the zeros is you don't have to look at your actual graph. You could go to second window, and I just wanted to point this out, and you could change your independent variable to ask, and then you could go to your table second graph, and notice that there's nothing in here. If you do have stuff in here, you could just hit delete to delete it out. But then you could test the numbers this way. So you could test all the numbers if you wanted to, negative 1, 1. But again, then you're spending more time trying to test the values rather than just looking at the screen to see, oh, well, we knew it was -5 and 2. But again, you can plug in all the values this way if you want. And then if you do that, it doesn't clear these values out for you. So the way that you clear them is just by hitting delete. So that's another way. But like I said, I always like to use the second trace value because I like to look at the graph when I find the zero. So that way I'm not spending too much time actually plugging in all the numbers. All right. So now that we have this, we can go ahead and let's now do our synthetic division, which is step 3. So for our synthetic division, you can pick whatever zero you want to start with. It doesn't matter. So you can do -5 or 2 because it will give you the same factoring solution in the end. So if we use -5 as our zero in the box, we are not missing any zero placeholders. And so we're just going to write our coefficients, 1, 3, -1, 27, and -90. We bring down that first term. So 1 times -5 is -5. Add those terms together to get -2. -2 times -5 is 10. Add those terms together to get 9. 9 times -5 is -45. Add those together to get -18. -18 times -5 is +90. And remember, that should always happen to get a remainder of 0. Because you're saying this is a root of your polynomial equation. So if you didn't get 0, that means either you plugged your equation wrong into your y equals, or you found the wrong zeros on your graph, or you did synthetic division wrong. So I always like to check what I plugged in my y equals first. So now that I have this is what we factored our equation into. So the factor of x minus 5 is x plus 5. And then remember, if this was a polynomial of degree 4, then when we do synthetic division, this would be degree 3. So this would be x cubed minus 2x squared plus 9x minus 18. Now that we have this, I see I have a polynomial of degree 4. So right here, we can factor this in order to find the other solutions because we know how to factor 4, but it doesn't necessarily mean that we can factor this. But if you don't remember how to factor this, you can do synthetic division again with your other 0 on this answer. So we'll do both. So I'm going to start off with synthetic division again. So if I synthetically divide this again using my other 0, which is 2, I'm going to use my answer that I just had. So -1, -2, 9, and -18, because you don't want to use the original one because you're trying to factor your polynomial as far as you can, which using your answer allows us to do that. So when I bring down the 1, 1 times 2 is 2. -2 plus 2 is 0. 0 times 2 is 0. Add that together to get 9. 9 times 2 is 18. Then again, you'll see you get a remainder of 0. Now, since we used our answer, which was a polynomial degree 3, that means our answer here is going to start off with x squared. So this would be x squared plus 0x plus 9. Of course, we don't need that 0x. So I'm going to write my factorization over here. So we first use the 0 of -5, so x plus 5 is the factor. Then we use 2, so x minus 2. And then this is x squared plus 9. So this is actually the factorization of the polynomial. That's what we're doing when we're doing synthetic division. So if I were to FOIL this out, I would get my original polynomial that we started off with. But again, it's not asking us to write the factored form. It's asking us to find all the zeros. So we set each of these factors equal to 0 and solve, but we already know this one is x equals -5, and we know this one is x equals 2 because that's where the actual rational roots were. So now we're just solving x squared plus 9 equals 0, so x squared equals -9. So x is equal to plus or minus the square root of -9, so x equals plus or minus 3i. And so that gives us our other 2 remaining zeros. So now we found all of the zeros, which is x equals -5, 2, and plus or minus 3i is 2 solutions. And we know that imaginary solutions have to come in pairs. So it makes sense that we have the plus and the minus of the 3i. And so that gives us all of our 4 solutions of our polynomial. Now I'm going to go back to this part of my equation. And remember I said you could also do factor by grouping if you remember how to do factor by grouping. So x cubed minus 2x squared plus 9x minus 18. So let's say I did factor by grouping instead. So I take out that first factor. I have x squared times x minus 2. And this would be plus 9 times x minus 2. So remember, these have to be the same in order to do factor by grouping. So we group our first terms, x squared plus 9, and then x minus 2 gets factored into the group. So notice that it gave us those same factors. This is the x squared minus 9, this is the x minus 2, and then this one, x plus 5, was from our first one. And so we get the same answer in the end. So it's just a preference. Like I said, if you remember how to do factor by grouping, you prefer to use that, that's fine if it works. And if it doesn't work, then you're going to have to do synthetic division. All right, so that is it for this problem. Let's go to the next one. All right, so for this problem, same thing. We're going to first find our possible rational roots, listing our p's over our q. So we have to find factors of the constant. Over factors of the leading coefficient, which is factors of constants are plus or minus 1 and plus or minus 3. And the constants, so that's constant. So the leading coefficient would be factors of 8, so plus or minus 1, 2, 4, and 8. So that means the possible rational roots are going to be plus or minus 1 and 3 over 1, so 1 and 3, 1 and 3 over 2, so 1/2 and 3/2, and then 1 and 3 over 4, so 1/4 and 3/4, and then 1 and 3 over 8, so 1/8 and 3/8. So these are all my possible rational roots. So for this one, the next thing I'm going to do is plug this into my y equals. So in my y equals, I have 8x to the 4th. Oops. Plus 2x cubed minus 21x squared minus 7x plus 3. All right, so now I have my equation in my y equals, and I'm going to hit zoom 6 for a standard window from x values from -10 to 10 and y values from -10 to 10. And this is a polynomial degree 4, which means I should have 4 total zeros when I'm done. And so the highest and lowest possible rational root is plus or minus 3, which a -10 to 10 is looking at the full window. So we know we're looking at a full window, and I can see I have 1, 2, 3, 4 zeros here. So I'm actually going to change my window, and I don't need to be all the way at -10, so I'm just going to do -5 to 5 to see if I can look at this a little bit better. And again, we know we're not looking at a full building window because I can't see that minimum over there, but we're just concerned about finding the zeros. So now if I'm looking at this window to find the zeros, I can see that it looks like I have 1 in between 0 and -1 and 0 and -2. So I'm going to try some of these values that I have over here. So second trace value. So in between -2 and -3. So if I look at my zeros over here, I know 1/2, if I did -1/2, that's not going to be in between that. This is -1.5, so let's do -3/2. Let's see if that works. And it does. So that means that this is -3/2. The other one I would try would, of course, be 3/4. Would not be in between. So it looks like the only one that we have is the 3/2. So -1.5. So our actual rational root, x equals -3/2. Then it looks like I have in between 0 and 1, so it's hard to tell what that is. So let's do second trace value. So if we do -0.5 or -1/2, notice we don't get 0, so that's not a 0. So second trace value. So let's see, we did -1/4, which is -0.25. Again, we don't get 0, so that's not it. So that was there. And if I try to do second trace value, -3/4, that's down here, so that one doesn't work. And if I try to do second trace value, -1/8, that also doesn't give us a 0. So second trace value, if we do 3/8, oh, negative 3/8, sorry, second trace value, negative 3/8 because we're on the negative side. Again, that does not work. So what does that mean for this root that I'm seeing here, but that is not one of these possibilities? So remember, these are just the possible rational roots of our equation, which means that this answer here that I'm seeing that I'm not getting one of these possible rational roots for is irrational. That means that tells me I'm going to know I'm going to have to use the quadratic formula at some point to find that answer. So that just means I can't use this as one of these numbers here. So irrational answers come in pairs. So that means that one of these others is also going to be irrational. We just don't know which one yet. So we're going to have to test here and here to see which one's the actual rational root, because I know I have one more. So let's do between 0 and 1. So second trace value, and it looks like it's less than a half. So let's maybe try 1/4 and see if that works. Oh, and it does. So 1/4 is the other 0, which means I know that this 0 in between 1 and 2 is going to have to be irrational, because again, irrational answers come in pairs. And so if you want to test the other ones just to make sure, you can, it's just more work. So now that I have this, then I can go ahead and do my synthetic division. And again, it doesn't matter which one you want to do synthetic division with first, you'll get the same answers in the end. So negative 3/2, if I put that in my box, I have then 8, 2, negative 21, negative 7, and 3. And again, if you're missing any 0 placeholders, even for the constant, you would always want to add that in. So 8 times negative 3/2, so 8 divided by 2 is 4, and so 4 times negative 3 would give us negative 12, and then add those together to get negative 10. Negative 10, because I'm multiplying it by negative 3/2, I'm just thinking about divided by the 2 first, so that would be negative 5, and negative 5 times negative 3 is 15. Add those together to get negative 6. Negative 6 times 3/2 would give me 9. Add those together to get 2, and 2 times negative 3/2 is negative 3. And that means, again, my remainder is 0, which is what we want. So then if I start off with my x's, this is degree 4. So that means that this would start off with degree 3. So 8x cubed minus 10x squared minus 6x plus 2. So if I can do factor by grouping, I can go ahead and try that to see if that works next. So if I try my factor by grouping, I can factor out here a 2x squared, and then that becomes 4x minus 5. And then over here, I can factor out, let's say, negative 2, and that would become 3x plus 1. But these are not the same, so that means that we cannot do factor by grouping. So since we can't do factor by grouping, that means we're going to have to use synthetic division with my other 0, because like I said, sometimes you can't always do factoring by grouping. So now we're just going to do synthetic division again with this answer with my other 0, which was 1/4, and that's going to factor my polynomial again. And you can rewrite it out if you want, but I'm just going to use the answer here to save some time. So the 8 comes down. So 8 times a fourth would give me 2. Negative 10 plus 2 is negative 8. 8 times a fourth, negative 8 times a fourth would be negative 2. Add those together to get negative 8, and negative 8 times a fourth would be, again, negative 2, and those give me the 0 for my remainder. And so we divided our polynomial twice. So that was start off with degree 4. This one was the x cubed degree 3. So that means this is going to be degree 2. So 8x squared minus 8x minus 8. So again, we're trying to find all the zeros. We have 2 of our zeros already, so we just need the other 2. So I know that since these are irrational, this is not going to be factorable, but if we try to factor, you can take out your greatest common factor of 8. So then that becomes x squared minus x, and then minus 1, but there's not factors of negative 1 that add up to negative 1, so that means we have to use the quadratic formula. So our A is 1, our B is negative 1, and C is also negative 1. So x equals negative, negative B, so negative, negative 1. plus or minus the square root of b squared, so negative 1 squared, minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a. And then we just want to simplify, so we get negative 1 is positive 1, plus or minus the square root of 1, and then that would be plus 4, so 5 over 2, and of course that doesn't simplify any further, so that means that all of the zeros are x equals negative 3/2, 1/4, and 1 plus or minus root 5 over 2. And so for this, just to show you, if I turn my calculator back on, I can do second trace value. If I plug in to my calculator 1 plus the square root of 5 and then divide that by 2, you'll notice that gives me my other zero. So remember we talked about 1 times e to the negative 12 just means 0, and you can see here because that's just moving your decimal place 12 places to the left, and you can see on your graph it's 0. So that tells me that is my other solution, and you could also do the negative as well, and that would give you the one over here. So that gives me all of my roots. So now this is a polynomial degree 4. I have all 4 solutions, so that therefore I know I'm done. So I would then pause the video now and just try to see if you can do this next one on your own, and then when you're done you can unpause to check your work. All right, so again, same thing. We're going to first list our possible rational roots. So p over q is factors of the constant over the leading coefficient. So plus or minus 1, 2, and plus or minus 1, 2, and 4. So p possible rational roots PRR would be plus or minus 1, 2, and then 1 and 2 over 2, which would give us 1/2. 2 over 2 is just 1, and then 1 and 2 over 4, so 1/4, and then 2 over 4 is just a half. So these are all our possible rational roots. Now we need to find the actual rational roots. The next thing is to plug it into your y equals, which I already have mine plugged in. So I'm going to go to zoom 6 for a standard window from negative 10 to 10, because the highest and lowest rational root we have is plus or minus 2. So I can see I have 1, 2, 3 roots here. So that means the other 2, since I can't see them, must be imaginary. So I'm going to go ahead and just zoom in on these so we can get a better feel for what the zeros may be. There's my 1, 2, and 3. So it looks like we have 1 in between negative 1 and 0. So right here, so let's do second trace value. It looks like it's more than a half, but it's kind of hard to see. So let's try, I guess, negative 1/2. Oops. Okay, so that doesn't work. So that must mean that this has to be an irrational root. So then let's look in between 0 and 1. It looks like it's bigger than a half as well. So if I do 0.5, that's not it. And I know it's not 1 because I can see. So that means these two roots are irrational, and that means that this one here, let's see, second trace value, if I hit 2, enter, yep. So the only actual rational root we have in this case is 2. So the actual rational root is x equals 2. So let's go ahead and do our synthetic division then. So we have 4, we're missing, so degree 5, 4, we're missing degree 3 and 2. So 4, negative 8, and we need a 0 placeholder for 0x cubed, and then 0x squared, because that's missing there, and then so minus 1 and 2. So don't forget to put those 0 placeholders in. Bring down the 4. 4 times 2 is 8. Add those together to get 0. Then 0 times 2 is 0, 0, 0, 0. So then this would be 2. So that would be 1. Sorry. So that would be 0 here. That's my fault. It's because 0 times 2 is 0. I wrote 2. And then this would be negative 1. And I knew I did something wrong because I know that answer. So remainder has to be 0. So negative 1 times 2 is negative 2, which is 0. All right, so this is a polynomial degree 5, so that means this is degree 4. So this would be 4x to the 4th plus 0x cubed plus 0x squared plus 0x minus 1. So we don't need the 0, so we have 4x to the 4th minus 1 equals 0. And so for this one, we can solve this by the difference of 2 squares. So we need to factor this. So this would be 2x squared minus 1 or plus 1, doesn't matter what order you do this in, and 2x squared minus 1 equals 0. So then we have to solve each factor. So 2x squared plus 1 equals 0. 2x squared minus 1 equals 0. So we get 2x squared equals negative 1 here, and 2x squared equals 1. Divide by 2, x squared equals negative 1 half. X squared here equals positive 1 half. And then we're getting rid of that even power, so we have to do plus or minus the square root of our answer. So x equals plus or minus the square root of negative 1 half here. X equals plus or minus the square root of positive 1 half. And then remember, we don't like fractions underneath radicals, so we need to rationalize this by multiplying by roots 2 over roots 2. Same thing over here. And I'm going to also take out that negative, so that becomes I. So then this would give us plus or minus root 2 over 2. And down here, we would get x equals plus or minus I root 2 over 2, because that negative means it's imaginary. And that gives me my other 4 solutions to my graph. So the other 2 that we have that were on here, so if we do second trace value, you can see square root of 2 divided by 2. That gives me this 0 here, and then if I were to do negative root 2 over 2, I would get the other 0. So it's just an easy way to check to see if you did that correctly. So then that means all the zeros are x equals our rational root, which was 2, and then our irrational roots plus or minus roots 2 over 2, and then our imaginary roots plus or minus I roots 2 over 2. And that gives us all 5 of our solutions. And that is it for the rational root theorem. So a lot of calculator steps that you have to be able to do here. So if you need any extra support with those, just make sure to come in at lunch and I can help you.